Go to participants, and somewhere there is a host,
Like claim host?
claim host. Okay. And claim host key is 103292.
All good to go.
Okay, thank you.
Yeah. So the camera, I think it's seeing the.
On the left.
Oh, it's flipped on my end.
Oh, so go to camera conference. There is the very bottom, there's an arrow right next to it.
Oh.
And settings. This. Is there a
There's a mirror video.
no? I don't think it's a mirror. Do you see any rotating symbol here? Usually there's a way to rotate. Okay, try the mirror. Is that straight?
Yeah, no.
Oh, so
now this
just
is over here now.
Oh, okay. So
Okay.
yeah, that's it.
Okay.
Thank you.
Yeah.
Okay, half an hour down, not 1 minute. 20 minutes down. We'll make it. I'll try to make it short. I'll try so that those who miss can. And because we miss this. The midterm is November 7. That's week. There's a new homework. Nine. And doesn't break the. Okay, that's it. So today, after we have done Green's function, I want to motivate what's the Green's function associated with a Laplacian, which is basically that of a point charge. So if you have a point charge or a point mass, what is the potential due to that? It was historically important because Newton gave his equations, and immediately the idea was, can we study planetary motion? That was the biggest, you can say, success, and the challenge also. You wanted to make it better and better. And basically, there is a mass, and you would like to know the potential associated with it. And there is a detail in there that, or one should point out that the electric potential or a gravitational potential due to a mass does not depend on the radius of the mass, right? There is no dependence on the shape. Like, it doesn't matter whether the Earth is elliptic or spherical, it will attract Moon exactly the same way, right? Is that clear? Because Newton's law of gravitation doesn't have the radius of Earth or the shape of Earth, nothing. It just has the mass. If it has the same mass, any object would have done that. If Earth was rectangular in shape, Moon will still behave exactly the same way as far as the center of mass is, right? Rectangular, or take any crazy shape you can think of, as far as the center of mass is at the same place, Moon will not change its behavior around us. The same thing with Sun. Sun's internal structure doesn't affect our motion. And that's all comes from the fact that what is the electric potential or the gravitational potential associated with a point mass or a point charge. And that's what we want to talk about, and then talk about details, how we can make it better. And that leads to the idea of Legendre polynomials we want to study. So today I want to introduce Legendre polynomials. Does anyone have a no?
Let's check and see if it.
Is it okay?
Yeah, it's visible.
Okay. Legendre polynomials. It's named after Legendre. It's a good thing to. It's a nice story associated with Legendre. Quiz is. I think for some time we did not have a quiz. Find a picture, a portrait of Legendre, and the story is that it doesn't exist. So the story is Legendre obviously was very famous, like it was during French Revolution. That's 1800 or so. And after about 30 or 40 years, there was a picture posted about him. And for 200 years, we have been using that picture forever. And recently, I think in 2003 or 2008, when computer graphics became very popular, some students noticed in computer graphics that there are two Legendres and both have the same picture. So somewhere 200 years back or 100, whenever that happened, the physicist Legendre's picture got replaced with a military personnel Legendre's picture. And now the question is, where is the picture of the original, the physicist Legendre? And apparently we don't have it. So that's a challenge. And historically, if you can find it, all these are usually difficult. It doesn't mean that it doesn't exist, but it's just a matter of finding it. Exactly like this picture got swapped. So somewhere that might be a picture which we don't know about, and we can figure that out. That's good. So yeah, it doesn't exist, but just read this up, look up Legendre's thing. There is a cartoon of that of him. So look up. Did you see it?
So that's
No, there shouldn't be any picture. Did you find the picture? Yeah, cartoon, right?
I'm sure the guy is mistaken.
Mistaken. Yeah.
Oh yeah,
Yeah, so that's the caricature of yeah. So apparently it's not. It's a nice story, and especially grad students found it. So they were computer science grad students. They were doing some project of computer science, and they figured out that, oh, this doesn't make sense. So it's an embarrassment for the community. For 200 years you were using the wrong picture, so it's surely an embarrassment. But yeah, so that's it. So the quiz is to find out what it is. And remember, only few sentences is sufficient. And we are not submitting online, so we just bring it here, and right before the class, you just give it to me. And I return it back in your mailboxes, right? I think all of us. Okay, so that's about Legendre. So, but what are Legendre polynomials? Let's begin. We have used the idea of Green's function, and I want to point out that the Green's function for Laplacian is 1 over r minus r prime. But let's just pretend that this is for a point mass. Gravitational potential, maybe? Yeah, gravitational electric potential. I like electric potential. you do a point charge is if you are measuring it at the observation point R, that is, what is that equal to? Electric potential due to a point, just one charge, Q by R, right? So it is 1 over 4 pi epsilon naught. And that is a Q. And when it is Q by R, you're assuming that it is at the origin, or you mean the distance between the observation charge and the charge. So let's make this R minus R prime, where R prime is the position of Q. What is epsilon naught? That is the electric property of vacuum, permittivity of vacuum. If you had a medium between the charge and the observer, then this changes and you have to bring in the property, electric property of the medium in there. So R is the observation. This is also the Green's function associated with the Laplacian, but for our purposes, just stick to this. And exactly what Roki said, like this is R, right? And I changed it to know, let's look at the details, and it is R minus R prime. So let's see, point out. So this is the diagram you can have, and this is charge. That's your charge. That means that's R prime. And the observer could be somewhere here, and that's your R. So everything depends on R minus R prime, so that's your R minus R prime. If the charge was at the origin, clearly there is a simplification, but you can only choose to keep a charge at the origin once. You cannot have every charge at the origin. Like usually the origin is occupied by one of the charges. Then when you bring in the second one, you have to keep it outside. And that complicates the problem. Then there is a clear, what I'm going to show, that it is not necessarily simple when you really consider this as a whole. So let's ask, what is R minus R prime? So what is R to begin with? R is, if you are working in rectangular coordinates, it's xi hat plus y j hat plus ck hat, and R prime will be x prime, y prime, z prime. So R minus R prime, and it is a magnitude that shows up. That's equal to square root of x minus x prime squared plus y minus y prime squared plus z minus z prime squared. Often you want to work in spherical polar coordinates, so we would like to do this discussion in spherical polar coordinates. R in spherical polar coordinates would be R sine theta cosine phi in the I hat direction plus R sine theta sine phi j hat direction or cosine theta. Remember, theta is with respect to z hat. Often in physics, it's reasonably consistent. Almost everyone chooses theta, the angle between the vector r and the z hat is what is chosen to be cosine theta. But almost consistently, all the mathematics textbooks will choose this as phi. So if you study all the coordinate geometry from mathematics, then you make sure that this is what the notation I'm using. It's a once you realize it, it's pretty straightforward. And the same thing now, how do I define my cosine phi? Let's say cosine phi is with respect to the x-axis. Let me not say. I think after that is reasonably clear. What about r prime? It's a new variable, so it is be r prime times sine theta prime. So there are three coordinates. I have cos r. That should be straightforward. And what is r dotted with r prime? Notice these are the two r and r prime. This depends on an angle theta. Maybe I should draw this if this was z-axis. This is z hat. And this is angle theta prime. And that's angle theta. They do not have to be in the same plane. They can be in different planes. So this could be making an angle between them. And what would be r dotted with r prime? Is equal to r times r prime times cosine of what? So what is r dotted with r prime?
This way.
No, r dotted with r prime is magnitude of r prime, and the cosine of the angle between them, right? A dotted with b, right? So what is the angle between r and r prime? 90. Why is it 90? So theta minus theta prime. Is there any issue with that? Is that correct? Like, is that clear what I'm doing? A vector A dotted with vector B is A times B times cosine of the angle between them, right? So let's say alpha, right? This is vector A, that's vector B. The angle between them is cosine alpha, right? That's the definition of A dotted with B. That's vector R, that's vector R prime. What's the dot product between them? The angle between them. But I didn't give you the angle between them. What I gave you is the angle it makes with respect to the z-axis. I gave you the angle between with respect to the z-axis. So what is the angle coming in here? Is that correct? I say that's wrong. Or at least it's not always correct. It's not general enough.
So in this case, we just do data. Yes.
If this is in the same plane, that's correct. But they don't have to be in the same plane. If both of them are in this whiteboard plane, then it is correct. But these two vectors can make the same angle, and it can be on a cone. Is that clear what I mean? Right? This is the charge could be in on the xz plane, and the observer could be on the yz plane. So then that doesn't work out. Okay. So in general, this is not true, and we have to now calculate what is that gamma, and that is really the challenge we are talking about, and that's why Legendre polynomials are used. So the question comes: what is the connection between this gamma and theta and theta prime? So that's pretty much, very simplistically speaking, that's what Legendre tries to do. We want to have a formal description of how to do this for wherever the charge is kept. But let's see, this is, so what is the connection between theta and phi prime? At least in this case, it is easy. And let's do that, right? What is r dotted with r prime is easy to calculate. How much is r dotted with r prime starting from here? A dotted with b, you multiply these two, and then add up together, right? Each one has an r and an r prime. And we have sine theta prime to sine phi prime plus sine theta prime sine phi. Oh, I wrote this wrong, right? You wrote this wrong? This here? So this should be sine phi prime. Right. So this is sine of phi and sine of phi prime plus cosine theta times cosine theta prime. Yeah. That's the same as r prime times sine theta prime. That's common in the first two terms. And you have the sine of phi prime plus sine of phi prime plus sine theta prime. Using double angle formula for in trigonometry, you can simplify this. What is this equal to? The quantity in parentheses. So it is cosine of phi minus phi prime. So that's it. So this is r prime. This is cosine phi minus phi prime plus cosine theta prime. And that whole thing we want to call this cosine of gamma. It better be cosine of gamma, right? There does exist an angle between r and r prime. It's just that it is not equal to theta minus theta prime, but there exists an angle. So whatever that angle is, that is the cosine of gamma prime or gamma. R and r prime cancel out, and cosine of gamma is equal to sine of theta prime, the sine of phi minus phi prime plus the sine of theta. Can this be simplified further? Not much, actually. You cannot use any trigonometric formulas to do that unless this appears completely. So there is not much simplification beyond this. But we would like to deal with it because usually when you're doing planetary systems or electric charges, these really one point charge doesn't have to be at the origin, and you want to do this analysis. But for simplicity, just for understanding what is going on, what we will do is that even though we will have it everywhere, let's begin with first theta and theta prime is all on the same line. Then we will move it at one angle. They're on different cones. And then in general, we will have theta and phi prime separate. So we would like to deal with this, but we will go in steps. So first step is the easiest one can do is everything is along a line. Let's say theta is equal to theta prime, and phi is equal to phi prime. In that case, phi is equal to phi prime makes this 1. The sine of gamma is equal to sine theta or sine square, right? So this is sine theta plus cosine theta cosine theta. How much is that? That's 1, exactly, right? So that's 1, and that means gamma is 0. So that's really the extreme case where it really things become simple. But let's do that anyway, just to motivate what is going on. We want to now release all these constraints, but to begin with, let's do this very simple scenario. If that is the case, if gamma is equal to 0, let's go back and analyze this. What is r minus r prime? This is r minus r prime. Magnitude is equal to square root of r minus r prime. Got it. The scalar, that's how you can build it. That's equal to r square, r dotted with r, plus r prime dotted with r prime, plus 2 times r prime, and a square root. That's the same as r square plus r prime square minus 2 times r prime times cosine of gamma, where cosine of gamma is this whole expression here. That complicated expression shows up in here. So if you're doing the electric potential due to a point charge and the charge is not at the origin, immediately there is this huge complication that comes in, not necessarily easy, or it's tedious. That's a problem. But we are doing the simple case where gamma is equal to 0. So when gamma is equal to 0, we have r minus r prime is equal to r square plus r prime square minus 2 r minus r prime, which is at this stage very simple. This is equal to, really this is a vector notice, but now this is just the length that matters. So, but that's a very special case when gamma is equal to 0. This is equal to r minus r prime if r prime was less than r, and this is equal to r prime minus r if r was less than r. There's a few of situations. What is your electric potential in that case? So potential, so phi of r for gamma equal to 0. Gamma 0, we have q over 4 pi epsilon naught, and 1 over r minus r prime. So let's start with r prime being less. So this is r minus r prime. So this is for the case. I'm doing the first case, and I'll come back and do the second case in a minute. This is the same as q over 4 pi epsilon naught, 1 over r times 1 over r prime minus r is less than 1. So maybe this can be expanded out. I would like it as a series. This is equal to, and I'm also saying prime is less than r. So it's a particular case. Is that clear until now what's going on? Yes. I want to write this as a series. So this is 4 pi epsilon naught and 1 over r. Of course, if r prime was 0, that means it is at the origin. You get back to your first expression that we started with. But if I want to expand this as a series, how much is that? So it is 1 over 1 minus x as a series. How much is it? 1. plus, what is the series? So maybe it's good for you to remember that 1 over x raised to n, for any n, it doesn't have to be an integer fraction. For any n, this is equal to 1 plus n times x plus n times n minus 1 over 2 factorial. So this is 1 factorial over x squared, and it keeps going, keeps subtracting, and then n plus r, and then the factorial comes in. So this will be, the power is minus 1. So this will be 1 plus minus 1 times minus x over 1 factorial. And the next one will be minus 1 times minus 2 over 2 factorial. And then there is minus x raised to square, and so on. And you clearly see that this is equal to 1 plus x squared plus so on. So every term is, the coefficient is 1. Use that in here. This means 1 plus r prime over r plus r prime over r the whole square plus so on. This is all for r prime less than r. We would now like to do this for r less than r prime. What will that be equal to? You again start from here. This time, instead of writing r minus r prime, you say r prime minus r, which is practically swapping r and r prime. That is the only thing that is happening. So I just have to swap the quantities here, and I get the answer for r less than r prime. So this will be equal to q over 4 pi epsilon naught 1 over r prime, and this is 1 plus r over r prime plus r over r prime square, and so on. You know, one would like to have this is, you have to write this twice. So just for that simple reason, let's say let's have a notation that I will call r less as the smaller of r and r prime. There are two variables. Whichever is smaller, I will call that r less. R greater would be larger of r and r prime. So in this set, whichever is larger, you will call it r greater and r less. Is that notation here? Is that a familiar notation, by the way? No? ENM, electromagnetism, or is it? Okay, that's fine. So we will. Okay. Sometimes it's some literature that is common, but otherwise it's a simple notation. Okay, so the electric potential due to a point charge for gamma equal to 0, right? That's a crucial big, almost it makes it trivial, is equal to q over 4 pi epsilon naught. And it is r or r prime. In this case, r is larger. In this case, r prime is larger. So it is a larger one that comes out. The larger one. And this quantity, the rest of the quantities is 1 plus the ratio of RL over R greater plus R. And so on. Okay. Now, if gamma is not equal to 0, this will get complicated very quickly, which we will show in a minute, at least for one scenario. But whatever this is, what will change is the coefficients. What is going to change is the coefficients in front here. Coefficients in front here, coefficients in front here, and they will all depend only on gamma. So if this is gamma is not equal to 0, this can be written as 1 over r greater, and let's call that 1 plus the first coefficient here. Actually, I should also have this very first one too, right? So this will be P0. That's the first term. Let's call that the sign of gamma. So whatever is the first coefficient will become dependent on gamma. The second one will be P1, the coefficient, which depends on gamma, times R plus. So clear what I don't know what these are. We have to find that out. And plus E2, the sine gamma, and plus greater square plus 1. Okay. Any questions? So this coefficients is what you define as Legendre polynomial. So so now we have EL of the sine of gamma, which we want to find out. This will be Legendre polynomials of order L. Clearly, L goes from 0, 1, 2, 3, and so on, which we will find out what that structure is. But we know one thing for sure, right? And gamma is equal to 0, so PL of the sine of 0 is 1. PL of 1 is equal to, how much is this equal to? PL of 1. There will be 1, right? All of them are 1. 1, 1, 1, 1. All of them are 1 independent of L. For every L, it is equal to 1. For L equal to 0, 1, 2, irrespective of what L is, they are all 1s. Quiz? Okay, maybe find out. Maybe can you answer this? Let's say PL of minus 1 is how much? When will this be minus 1? The sign of what is minus 1? The sign of pi. So can you tell me what will PL minus 1 be? When will that happen in that figure? So 180 degrees means that, so remember when this happened, there was a point chart. We had a coordinate system. We're talking about a point chart. This is R prime. Right, that's your point chart. And our observation point was somewhere here. That's your R. From here to here is R. R minus, if everything is on a line, then theta is equal to theta prime, phi is equal to phi prime. And R minus R prime. And we have been restricting our scenario all along this line. But I can have my observer all the way across on that side. That's 180 degrees. But that is easy to do because that's just r plus r prime, right? So r minus r prime. So for PL minus 1, we are basically, so if we are figuring out what that is equal to, phi of r for gamma equal to pi, right, is equal to 1 q over 4 pi epsilon naught. What comes in here? What is the denominator? In this scenario, when the observer point is along the same line having the origin in it, what is this? What is this denominator here? What is this equal to? R plus R prime, right? Is that clear? Because it's along a straight line, so it's opposite, so it is R plus R prime. You can expand this out again, right? So it doesn't matter which one you pull in. So this is Q over 4 pi epsilon naught. Let's say 1 over R, and this will be, first term will be minus, right? 1 minus R prime over R plus R prime over R square, and so on. Is that correct? Remember, so this is instead of minus, this becomes a plus. If this becomes a plus, that's plus. Right? And that seems to suggest that there is a minus 1 in the odd terms. So this seems to suggest that this would be equal to minus 1 raised to L. Right? Just based on that. So it is very easy to get special cases of these quantities, but we would like to have a little more generic formula. So in general, what that is equal to. And also notice it is the whole cosine of gamma it depends on. It is not gamma alone it depends on. So sometimes it is easy to think of x as cosine gamma. So what are the values x will take? Gamma goes from anywhere between 0 to pi. Right? That's the maximum it can go. And that's mostly because once it crosses pi, it will start repeating again. So x goes between +1 to -1, and it can be equal. So Legendre polynomials will be polynomials are PL so we haven't defined it, right? No, we did define it. Right? I think so. Yeah. So the definition of Legendre polynomial will be 1 over 1 minus, say, r less over r greater. Expand this out as summation of L equal to 0 to infinity, and PL of L. Let's write it. And I didn't write this correct. We write this 1 over L. Let me just say so that whole thing will be your definition of Legendre polynomial. So I should write instead of theta, that's your gamma. We want to do this in general, so let me motivate at least how you would proceed if it was more, if we don't have these special cases involved. Let us consider the case. So 1 over r minus r prime is surely equal to 1 over r squared plus r prime squared minus 2 r prime times the sine of gamma. That's for sure. Let's have the 1 over r greater pulled out. This is equal. Let's pretend that it is r, so it will be 1 plus r less r greater square minus of 2 times r less over r greater times the sine gamma. Let's have a notation here that x be equal to cosine of gamma and t be equal to r less over r greater. Then what we have is 1 over r greater. This is equal to 1 plus t squared minus 2t times x. And I would like to expand this out as an expansion in t now equal to 0 to infinity t raised to l times t of x. It's just doing some notations and exactly the same thing. I have not done anything new. It's just rewriting the same idea. This is called the generating function of the Legendre polynomials, primarily because it generates all the, like the coefficients are basically the Legendre polynomials. So if I expand this out in this form, each coefficient I just have to collect. And let's do that for at least a couple of terms here. So I start from, so clearly the generating function is, so this is generating function of Legendre polynomials is, so you say this is G, generating function, X T, don't use typically write it as T, so it doesn't matter. It's 1 plus T squared minus 2T X. And one should see the motivation behind it. You're working on planetary motion, and that's your potential. You want to get more and more accurate. Right? Imagine trigonometry 2000 years back. Sine function is basically a series. And if you want to do any trigonometry and do any calculations, you want sine of 30 degrees to be as precise as possible. Let's say sine of 60. And in 180, sine of an angle was known only to one significant digit. And it was very tedious to do for an arbitrary angles. Does anyone know how you calculate sine of an angle? Let's say sine of 15 degrees. How would you calculate that? Sometimes you study this in high school.
So I got the opposite over the opposite triangle. For the arc.
Yeah, but the idea is that that will require measurements, right?
Yeah.
So the idea is without measurements. So you really want to have sine of 60 degrees. Or let's say sine of 15 degrees. So the idea is, sine of 90 is 1, you can use that. And some special cases you can use. And then in terms of that, you have to calculate. So you have to use double angle formula to do that. And first time this was done, like let's say when astronomy, we are talking about 180 during the time of Ptolemy, when things were reasonably precise, like astronomy was predictable to good, let us say within 1 hour, you would know exactly which planet is going to come in which place. And in those times, you want angles to be reasonably precise, but trigonometric relations were not available up to 7 degrees. If you look at Ptolemy's notebook, the best you could have, so there is a table you will have sine of 7, sine of 7.5, then sine of 15, sine of 22.5, sine of 30. That is all the values you have. So you only have 7-degree resolution. Now we have as much resolution as we want because we have computers and calculators. But in those days, there was a table, which was a sheet of paper, in which these were the only angles available. If you wanted to go further, you had to do a lot more work. So it was quite tedious to do this calculation. We are in a similar situation. We would like to make this more precise, right? More you go into the series, more accurate you're getting. So you're doing planetary motion, and if you get these polynomials to higher orders, that's great. But first you need to have a procedure to get that. And that's exactly what I'm going to do. I'll show you the tedious way of doing it. But later we have learned recurrence relations for that. And now we have all the properties in an integral form to do that. But we are at this point defining Legendre polynomial. And the motivation behind is to study planetary motion. That's reasonably what it is, as accurately as you can in those days. So in this case, first we have L equal to, when x is equal to 0, we have, right? So let's expand this for just expand it as well. 1 over 1 plus, treat this as a single object, so it is minus 2px. That's equal to 1 plus e squared minus 2px raised to minus 1. That's an expansion I just told you how to work on. This is equal to 1 minus of e squared minus 2px. Next one is plus minus 1 times minus 2 divided by 2 factorial. Minus 1 is 2. X the whole square. And if you want, this is, am I doing this correct? Mistake, right? Yeah, I'm making a mistake because this is a square root, right? So the coefficients are not having to be combined. So yeah, so this is minus half, right? Sorry, other, because the generating function has a square root of 2. So then things are slightly different. So let me redo that. So that's 1 plus minus half this time, and t squared minus 2tx, and plus minus half times minus half minus 1 divided by 2 factorial and t square minus 2tx square and so on. I'm just going to get the coefficient of t here. So I would like to, so this what I'm going to get is coefficient of t L equal to 1, right? I already have L equal to 0, so what it will be L equal to 1. So this is 1. And where can I get a t? I can get a t here. Is there a t there? T power raised to 1. The first is t raised to 4, then there is t squared, and there is a, that is t cubed, right? So there is no t raised to 1 here. And you can check that all higher ones will not have. So that's the only place where it comes. So it is minus and a minus plus, 2 cancels out, and it is t times x plus there will be t squared, and we would like to know what that is, and higher orders. So I have got the first term. So clearly, if I were to compare these two, I have p0 of x is equal to how much? And p1, this is L equal to 0. This is L equal to 1. How much are these two? What is p0 of x? Right, that's 1 because I'm comparing with this, right? This series, or if you want this series in here. So that's 1. And p1 of x is x, right? That's just x. Right. Quiz, find out p2 of x. So you have to find out the coefficient of this. So do the expansion again. Make sure that you capture all the t squared. This might also have t squared in it. So find out p2 of x. And in principle, you keep going. So it's very tedious, but that's exactly how you calculate. And then we will find out more efficient ways of finding the Legendre polynomials. So this is Legendre polynomial of order 0. This is Legendre polynomial of first order, and so on. We'll stop here and we will continue. You can just end it. There could be a cross button somewhere at the bottom right.